Okay, so in this video, I just want to give I want to talk a little bit more about conservative vector fields. So let's say that the vector field satisfies property 1, which is going to be that f is conservative, that is equal to the gradient of f. Then let's come over here. The fundamental theorem of line integrals tells us the following. It says that if this is a point v0 and this is a point v1, and we look at any path from v0 to v1, then we know that the line integral over any path from v0 to v1, we know that any line integral over any path from v0 to v1 we know that this is equal to f of v1 minus f of v0. Okay, and even because it satisfies the fundamental theorem of line integrals, we don't have to mention the curve that we're integrating over. We just have to put the starting position and the ending position on the integral. So this is a new piece of notation that we can use, and this is just shorthand for the following: CF, where C is any curve going from v0 to v1. Okay, this is what the fundamental theorem of line integrals tells us. And we saw before that another way to say that is to say that f is path independent, meaning that it doesn't matter that if you look at the line integral on any path connecting the points v1 and v2, it doesn't matter which path you take, the line integral is always going to be the same. Okay, now another thing that this tells us, another thing that it tells us is that the integral of f, the line integral of f over any closed path is equal to 0. So let's think about why that's true. Okay, so now this is some new notation. So what I'm saying is a new notation, a new term. So the line integral of f, if f is conservative, the line integral of f over any closed curve is equal to 0. So what do I mean by that? Well, a closed curve is a curve whose starting point and ending point are equal to each other. Okay, so its starting point is the same as its ending point. So it just makes a loop. Okay, so let's say this is v naught. Then what I'm saying is you have some curve that does like this and ends here. So v naught is equal to v1. Okay, and so when C is a closed curve, we put a little loop here, meaning that it is a closed curve. Okay, so by the fundamental theorem of line integrals, this is equal to f of v1 minus f of v0. But f of v1 is equal to f of v0 because v1 is equal to v0. Okay, so what this tells us is that the line integral of f over any closed loop is equal to 0. Okay, now it's actually not too hard to show this. I will let you all think about this on your own. It's not too hard to show that if property 3 is true, then really property 2 is also true. Okay, and it is a little more difficult to show that if property 2 is true, then property 1 is true. But these are in the book. I just want to go over them now. I just want to tell you them. Okay, and so the way that we say this is that these three statements are equivalent. In other words, if one of them is true, then the other two is true. If f is conservative, by the fundamental theorem of line integrals, 2 and 3 are true. Okay, if 2 is true, then we can show that 3 is true. If 3 is true, we can show that 2 is true. And if 2 is true, we can show that 1 is true. I know that was kind of a lot to take in, but we'll talk about this a little bit in class, and you can read about it in the book. Okay, finally, there's this one last very important property that I want to mention that's related to all of this. So this is kind of the most important property of this video from a practical standpoint. So let's just slow down a little bit. Let's say we have some vector field, and for now we're just going to look at a vector field on R2. What we're saying also works for three-dimensional vector fields, but it's easier to just talk about two-dimensional vector fields for now. So let's say this is a two-dimensional vector field like this, okay? Now, if this is conservative, then this is equal to the gradient of some function f. So what this tells us is that p is equal to the partial derivative of f with respect to x, and q is equal to the partial derivative of f with respect to y, because that's what it means. That's what it means for this vector to be the gradient of f. Now notice also that the partial derivative of p with respect to y is equal to the following. Okay, that's just because p is equal to the partial derivative of f with respect to x, so this formula is true. Okay, and similarly, we know that the partial derivative, we know that this is equal to the partial derivative of q with respect to x. Okay, but now by Clairaut's theorem, we know that these two things are true. Okay, so what this tells us is that the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. So in other words, if one is true, in other words, if f is conservative, then we know that the following. We know that the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. And we're actually going to show this in the next video, that if this fact is true, then f is conservative. And this is going to be a very practical thing we use to be able to actually use the fundamental theorem of line integrals. This will tell us whether or not the vector field is conservative. So in other words, whether or not we can use the fundamental theorem of line integrals, and it will give us a way to come up with a potential function. And that's what we're going to talk about in the next video. But the content of this video is just to understand that these four things are all equivalent. If a vector field satisfies one of these properties, it satisfies the other three of these properties. Okay, so we'll talk more about this in class, and you can read more about it in the book.